In this video, we are going to take a look at finding volume using the cross-sections method. The learning target we're going to focus on is finding the volume of a solid with known cross-sections. There are no Khan Academy videos for this particular topic, and it is somewhat of a rare volume technique because it doesn't involve revolution. Instead, it involves taking a geometric shape and basically popping it out of the graph. So rather than rotating around some horizontal or vertical line, you are taking your region and saying, I'm going to pop out squares or rectangles, almost like a pop-up book would be. So when it comes to disk and washer methods, we use the geometric formula pi r squared times height, where our radius is represented by the function, and in disk we only have to worry about the function itself because there's no gap, and in washer we have an outer and an inner radius. Volume by cross sections is also a method that we use when we are talking about cross-sections that run perpendicular to the axis we're revolving around. So volume by cross-sections is going to be done when we revolve, well, not when we revolve. In fact, I really shouldn't even have the word revolution there. But when our region is perpendicular to the x-axis or another horizontal line. But it is much different in the sense that because we're not revolving, we simply use area formulas. So you can see the formula here, and we'll talk about that shortly when we look at some examples. But to do volume by cross sections, you simply integrate over the region you're looking at from A to B, and you use the area formula for the specified cross section. The 4 cross sections that you are expected to know for the AP exam are squares, rectangles, semicircles, and equilateral triangles. The equilateral triangles are rare, but they have shown up in the past. It's more common that you would see squares or rectangles and possibly semicircles. We'll talk about where those formulas come from as we look at some examples. So volume by cross sections is actually derived from the idea of the volume of a disk. So if we recall, the volume of a disk is pi times the integral from a to b of our radius squared dx. And again, that's based on the geometric formula pi r squared times height, because ultimately our disks are every thin cylinder in a region combined. We can take this method and generalize it to solids of any shape, as long as you know a formula for the area of an arbitrary cross-section. As I mentioned, squares, rectangles, triangles, and semicircles are the shapes that you're expected to know. So, the volume using cross-sections, as mentioned earlier, is the integral from a to b of the area of the specified cross-section dx, where dx represents the width. This gives us a volume because area has a units squared label with it, times dx representing the width gives us those cubic units that we're looking for. These are the same formulas that are on the back of the Unit 8 curriculum map. And you'll notice that I use the word base in every one of them. As we look at the example here, you'll see where that idea of a base comes from. So, suppose a region is bounded by f of x equals 1 minus x over 2, g of x equals negative 1 plus x over 2, and x equals 0. Set up, but do not solve, the expression to find the volume of the region created when cross-sections perpendicular to the x-axis are squares, rectangles with height double the length of the base, semicircles, and equilateral triangles. So, as with any area or volume problem, the first thing we want to do is get an idea of what our region looks like. So I have a graph over here, and this curve, no, my mistake, this line is the line 1 minus x over 2. And it's kind of disguised, but it's actually in slope-intercept form. So 1 is our y-intercept, and negative x over 2 is our slope, so negative 1/2. So my y-intercept is 1. If I go down 1, right 2, that's how I get that line. The other line, y equals negative 1 plus x over 2, has a y-intercept of negative 1 and a slope of 1/2. So I start at negative 1, go up 1, right 2, and then I can see my region. So I'm looking at the region bound by the y-axis and those two lines. So it looks like a equilateral triangle, not to be mistaken with the one we're going to mention in Part D. And whereas with discs and washers we would be revolving this, we are not revolving it. What we are literally doing is saying, let's take any cross section here and let's pop it out so it comes up out of the screen. You can almost visualize if you had the region and I'll go with red this time. If this was the base that I use for one of my shapes, if I wanted to do squares, you would imagine this region popping out as a square. And then I could take any other cross section and pop it out as a square, so that all of my squares would make a solid. And you can see as I go further to the right, my squares get smaller and smaller and smaller. So it becomes this kind of rigid three-dimensional figure. So if I was doing Part A, all I would have to do is the integral from 0 to 2, because those are the x values of my region, of the area formula for squares dx. So the formula for the area of a square is base times height, where the base and the height are the same. So where does the base come from? Top function minus bottom function. So you can see down here the length of the base. I take my top function, 1 minus x over 2, and I subtract my bottom function, negative 1 minus x over 2, and I simplify. So 1 minus negative 1 becomes 2, and negative 1/2 x plus 1/2 x. Oh, I'm sorry, that should be a plus sign there. Negative 1/2 x minus another 1/2 x is essentially negative 1x, which is where the 2 minus x comes from. So from F to G, that distance of my base is 2 minus x. So the area of my square would be 2 minus x times 2 minus x, or 2 minus x squared. So if I wanted to find the volume of this entire figure using squares for cross sections, it would be the integral from 0 to 2 of my base, 2 minus x squared dx. We're just setting these up, not solving them, so that's all you would have to do. What about rectangles? Well, rectangles, it would have to tell you in the problem what the height is. So it's always going to be some multiple of the base. In this case, rectangles with a height double the length of the base. So my region here is the same, as is my base. My base is still top function minus bottom function. So if I was going to take a rectangle and draw it in there, my base is still here, but my height is double that. So you got to imagine a big rectangle popping out, and I could do that with every cross section. As I go to the left again, or right, excuse me, they would get smaller and smaller, but my heights would still be double. So how do I set up the integral? It's still the integral from 0 to 2, but think about what my rectangles are. My base is still that 2 minus x, but my height is double that, so 2 times 2 minus x. So the area of a rectangle is base times height, so it would be 2 minus x times 2 times 2 minus x, or 2 times 2 minus x squared. And you can see in my answer that I popped that 2 out front, so it's 2 times the integral from 0 to 2 of my base, 2 minus x squared dx. Very similar to a square, but the coefficient that we use for our height goes out front of our integral. Semicircles. Semicircles are a little bit more complex, because if I were to draw in a semicircle where my base is this region, then it would be like a little half circle popping up out of every region. So how do you find the area of a semicircle? Well, the area of a circle is pi r squared. So for a semicircle, it's 1/2 times pi r squared. The catch with this one is that your radius is only half of the base. So if I scroll up here, the area of a semicircle is 1/2 pi r squared, but because the radius is only half of the base, then it simplifies to 1/8 pi times the base squared. You can see that a little bit better here on the back of the curriculum map. So if I put a 1/2 times the base in here, and I squared it, 1/2 times 1/2 is 1/4, times the 1/2 out front gives me the 1/8, and then it just becomes my base squared. Once you know the formula, it's easy to set up. 1/8 pi times the integral from 0 to 2 of my base squared dx. Equilateral triangles, very similar. You would have to know the area equation for an equilateral triangle. It's not a common one that we use all the time, and I'm not going to derive it in the video here, but ultimately if we go up here, it is the square root of 3/4 times the base squared. And you could derive it by drawing any equilateral triangle and using Pythagorean's theorem to do 1/2 times the base times the height, and you would see how it works out, but again, that's not something we're going to derive in this video. So if I were to draw equilateral triangles where my base is here, then I would have my other two parts of the triangle with the same length as the base coming out, and all of them combined would make that rigid figure. So the volume would be square root of 3/4 out front times the integral from 0 to 2 of my base squared dx. More than likely, on an AP test, you would be asked to do a cross-section question involving squares or rectangles. Semicircles may pop up, and it's very rare, but it could happen that equilateral triangles do.